Good. So today, let's see. Thank you for Halloween idea with and sharing administrative things. A reflection. Your second problem set next Monday. It was supposed to be next Thursday. I think if I'm putting the room right next to loops, I'm trapped in room right now with who aren't entirely supposed to be learning loop at the moment. Is a fair read of people in the room? Okay. You'll have to get to it. Don't get me wrong. The next problem set we're going to get from Monday to a full set of Monday to just give you a couple to work on it, just of the difficulty people have with this sort of topic. We'll post that effect on Twitter, but the next set is coming out. Today we're talking about uncertain information. It's another fascinating element. Actually, one of my ideas of the lecture. Some of the lecture forward to the entertaining bit. Forward to a couple particular points that I want to say. So I want to lead with the question asked today is not estimated, but how can I get certainty estimate on effect? How can I get a marker? Okay, that's the question with today. To our answer, confidence. But before we develop confidence interval itself, I want to walk computations that exist to confidence interval. We're not based on a particular estimate of a give real margins of error, margin of error, particular that we're looking at. What kind, if you continue this field, point estimating an estimate prediction of really pretty easy. Get an estimate of uncertainty often pretty high. This turns out to be difficult then because it involves conveying information about your answer, which involves assumption identifying things in nature you don't. Talk about how computationally today using the bootstrap. Going back just to this, a couple of years after I started teaching in 2013 or 14, but we were using the 2000 action. On the left is neighbor who has since turned into a patron saint for social science dweebs. On the right is Joe Scarborough, who still has an MSN show for 5 in the mornings. But the fight that between that cycle and arguments between people who could use numbers to the future and you had to rely on wishes and numbers. Okay. Having been with me for 7 or 8 weeks, where I fall on the spectrum, but a lot of things involve showing that you're doing it. In this case, prior to the election, nature here on the left are all these different simulations. This on a website 538. Predictive simulations on election outcomes. He's actually from the university as an economist interested in metrics, which is sports outcomes. All those same betting ideas brings them over to politics. They adjusted nuances, but models, so they're basically models. Predicted 74 probability that Obama would win the 12 race and a 20% chance for me. Joe Scarborough, anybody that this race is a toss-up right, such an idiot jokes. And his certainty is his understanding. What's going on is we're going to how not just estimate the election, but it are uncertain. These were our results. This slide, and just to read the polls state, and then took the standard deviation for each state. Then for state, we drew random normal with mean and standard deviation. If that variable fell 50%, those elections to Romney, we gave them to. We ended up doing simulate tens of elections. All predictions were predicted for each. And what you'll note, we get this distribution of electoral from the Obama, the 196, 141 corresponds roughly to this point. And we actually 97 chance of Obama. And Silver got a little bit low. I might in lecture, he has 2% error on just as a matter of we didn't. The point being that what you've done in this class come off close to predictive model using simulation groups. That ideas that mean out in the problem. You're able to predictate things and how they do and do the chance to predictions and what predictions do. They capture our by simulating different elections carried through the in the for each state into our for the general. There's a finer point adjusted for to the model here, but it was pretty close. The adjustments were separate corrections, shorter ones. It was 2000, which was kind of a good year for data political science. 2006, which was a race Hillary Clinton Trump. If you missed it, it turns out everyone thought Hillary was going to win. In fact, did not. So one of the people in this was Wayne, who's here. He had the same estimate as everybody else. The exact point estimate was, but he didn't work his uncertainty. The detail procedures where you simulate elections in your care certain day. He ended up giving Clinton a 9.9% chance of winning in 2006, which was not correct. After the election, if Hillary Clinton win this, I will lead a minority color. So there is an art of social differs from neurobiology. Okay. The nature of his point is agreed with else. Everyone estimates that Clinton was a favorite batch on average. The question is certain. Sam Wayne odds of about 1,000 to 1 would win. The day of the election, Silver, betting on very forms of uncertainty, and closer to 1 for Trump. So with the odds close to 83 and 999, right? It's about a 1 in 16 prediction. The reason it's close to uncertainty. Okay. There's a big difference in saying this is a favorite plus 1% and this person plus or minus 8%. Right. In this lecture, breaking the idea, how do we get those minus? Be honest there and construct these uncertain estimates. For a set mortem reflect 2006 predictions, there's a and then we've talked a little bit in this. What was introduced what's called the interval, which is to adopt as our estimate certainty. Right now, we're going to construct and how to construct it numerically, construct computationally. Next level to this theoretical. But I build up an image of what a marker is telling us. If I single variable, confident the 9% interval is I have a single variable and I have its standard. The confidence interval is plus or minus 95% confidence interval plus or minus 0.9 standard errors. 0.96 We'll get to that. Just take this idea, confidence interval estimate plus or minus number of standard. Calibrating the number we'll talk, but for now, the fact that it's the estimate or minus sum. Okay, we're going to use this as our interval throughout the course. The standard deviation of the sample. So in this case, standard deviation x divided square root of x. We'll write that down next a little bit too. What confidence in tell us? It tells us two things. The first is that a repeated cells, we'd expect 5% sample means to that interval. So on a POL if we were to get 1,000 times, we expect 950 of the samples to fall in. That's useful because if I were to do it over and over and over, what like the results? The way to carry the confidence is an interval. It's not a single. Here's a where I think the sample is likely to fall. A second equivalent that we'll get to in the next lecture. This idea of we have a 95% confidence. That's the standard social science. Use 95 and sometimes percent. But a 90% confidence will contain value in 90% of stuff. So let me break that. Let's say you run 20 on the same. You get a confidence interval for 90 of those confidence will contain the value that you're trying. One of them won't. The nature of our this is a particular science because given study, we don't know the confidence contains the truth because we don't know what it is. We can say over repeat studies that are done, we start to see confidence intervals entirely a zero on 3, 4 studies, then we believe that there's an effect. Model of science relies on one then following up. Interestingly, in high levels in the social sciences, you'll have with different data testing the same hypothesis. Because there's a chance you'll get a positive in one, but finding data sets is much likely. So the idea is that in the same study, the confidence will either does contain the truth, no, but overall studies we use evidence the same topic build up an a few different intervals we have here. The 90 confidence is the sample plus or minus 6.4 stars. The 90% confidence interval is the plus or minus 0.96. The 9% is the sample mean minus 2.8. Take those numbers and we'll come back and show you where they come from. Generally, in 1.9x, most people just do close enough. If you have an extra point more to prove you assume that you're taking your case well. So it turns out often like on the quiz coming up when I ask constructed 90 confidence interval, it's plus or minus standard error. I'm not going to ask you things by 1.6. Multiplying by 2, people just 2. Let's see. Just like as an uncertainty on a sample. What do I think the electoral vote going to get? Popularity in a poll, something. Often, just as it did, or more interesting, not to say what's the group, but to compare. A shift from constructing a interval on a mean to a interval on a means. Okay. Here's group B has a mean. Has a mean. Can we estimate the difference and get error this interval on difference? A couple of choices: gender, public opinion, or that's a paper we'd used years ago. The difference treatment and control experiment, one we're going to talk here. Field experiment in political science, they were actually around the 1920s. They were popular in the 20s, then they just disappeared in the Depression season. And then they in the late 90s with the fame by Don and Gerber. I think it came from Slate. These can rise out of Ronald Green and two political scientists at Yale look at the vote, how this voter turn considered the voter mobilization efforts. Green, Gerber, and colleagues randomized field experiments to test techniques for real election. Subject the turn to a given robocalls, direct mail canvassing, etc. They use statistical analysis to determine voters in the true behave different from voters in the control group. So the question, authors interested in the 10 or 15 question produced some people saying question, what's active at vote, and what's at changing votes. They literally do little. This first look at was done in New Haven because voters were at the time. They went to New Haven, randomized, people got encouragements to vote, and which not, because they randomized, they can't make a difference in the idea is trying to do a little bit of scientific campaign. This is going to candidate one another, yes or no? Well, as an experiment. Some done that as a census, where during an cycle they'll go to their home and like this area, this canvas, it's that one, and they'll make results afterwards. It's easy to do in an A where voter is public. It turns out to be something you can do. We focus on a further 1990 experiment and come across, and the author had some great success. It was Rick Perry, running for governor, hired them as part of his campaign to run experiments about Texas to own his technique, and a lot of them adopted. So first experiment, randomized experiment, a respondent randomly assigned a control group or to receive phone calls or visited it. For the phone callings or visited person, they also has the message that we're going to allow point for the moment. But you can see the basic. Some people were randomized into treatment of one, others weren't. The outcome of the person vote. So what we're going to do is look at the interval of having been visited. So someone knocks on your door to do that, like the door for fundraising campaigns, right? Is that something that's still cool? Okay. So does right that, or at least did it behave, and our validity come into play, obviously. So confidence in the effect of having visited. We can calculate out for those who visited. For those who visited, turnout was 437. For the group that received treatment, turnout was 399. So visiting person had a 9% increase in probability of vote. Oh, that's good the way we expect to be, right? We can't deter people voting. What we want is estimated, this estimated enough such that we include its possible. Okay. A way of saying is this 9% plus or minus 3.9 points plus 10. 8.9% points plus or minus, then canvas probably campaign should people canvas if or minus 10 elsewhere. The sort of question asked me. Now, what we're going to do is take the uncertainty in our sample computation technique called the. We took this towards the end. Sure, last time I get into it a little bit now. Strapping is the way, but you'll see it works, and I hope it's an intuition, the uncertainty estimate. The bootstrap is we take observed sample and we're create a sample, same size sampling placement. An idea, let's observe x1, 2, x4, and whatever those are. Our bootstraps, well, we're going to see 5 of these with replacement. So they show up more and some are going to show up at all. What we're doing is we're our observed sample, but this could have this also been our sample, or this been our sample. And at the sample certainty in our, we generate boot samples that have been our observable, calculate the p from that. Let's say we observe this, then we play this mean, and we calculate for each one of these and use to generate our. So we're going to get the difference in mean back to each boot sample, repeat the loop, and 85% confidence interval is going to be 2.5 percentile to the 7.5 percentile. Folks see there's 90% in the middle, right? For an example. Well, this example you can try, and then we'll on the data that we're just talking about. In this case, let's say we observe data 3, 7, 9, 150. Want to know just what it's missed, but an estimate around. So what we do is create different bootstraps. What bootstraps are, we're going to sample indices with placement, and then to create variables, and I'll have code for the moment. So in this, let's say our bootstraps 3, 9, 3. Okay. And one is 7, 50, 11, 11. This is a fix this time. First bootstrap 5.8, our second one 7.2. We'll do that process over and over again 10 times. And then after the 90, this 2.5 percentile, 97th percentile to get our uncertainty. So let's go through. Let's just variable. Okay, let's variable x is going to 3, 7, 9, 11, and 150. And we're going to contrive to pretty quick screen, then we'll go to Gerber and some. So in this case, the mean contained to establish null. We're going to put them, okay, we need to declare this variable. We're going to do this 1,000. Then what we're going to do, a command called sample, if you set it this, it's going to take the x, take of x sample, replace equals, do it with replace. So we're going to take x, we're going to split with replace. We're going to take the mean of that strap sample in the container. And then we're going to do that again and again and again and do it times. That captures certainty in our. The bootstrapping us to do is here's our observable, but let's characterize off other we could have what the mean would be. And we take constructed hypothetical means to give us a bit of our uncertainty at the 2.5 tile and the 9.5. If we want to use the bootstrap, bootstrap mean dot going to contain a numbers being an S of one of the bootstraps. So 1,000 different in here. The bootstrap is just going to be mean of all the estimates. You just take the mean of. Want to know the error of the same? We can just standard deviate those means. So what we're treating means as different studies can see. Here you get the confidence of the 95th percentile and 90th percentile. We use the quantile R, which I do illustrated in handouts, and we're going to take the sample we generate from the strap, and we're going to take the half percentile, 97th percentile. That's our 90% confidence. For 30% confidence, we're going to take percentile 95th percentile, 5% below, 5% above. Intuition, we head into this on the act. The intuition is we need to somehow get certainty into our. If I have a sample mean, it's just a number. There's no right a single number. Example, I get a number. I want to know is if I have a different sample, what I get, and a different one I get, and a different what I get, a different one and a different one. And that bootstrap is allowed to do. And a single I now get an entire range or an distribution of it. That's where we get our estimates. So handle this in this Gerber and Green that we just talked about, where voted is a variable that's whether they're in 98, and this is subject to whether they're control group or they're in certain. Some people with multiple treatments, we're only going to take people who zero treatment, compare them to people who only visited. Okay, subset at that. We're going to call treat person, which is whether it's whether they were in person, for whether visited in person, whether they're in the control group. So these variables are subsets. Code is here. The code it shows set. If you want to see people voted, 607 voted, 609 not. Variable the treatment variable, 12 in the treatment, 5,006 in the control group. That two variables. You want to know between the treatment and control, and what's our error. In order to get to work, we set the count 1, get to work for the counters. That's what's being here. So we're going to set equal to 1. This seed, add if that command shows. What that seed is, it's going to make applicable. So we'll get, if we both the same seed, we'll get exactly the same from the bootstrap. It tells R the random number to the same application. So what we're going to do is we're going to draw an indices for n of n with these are the indices that are going to come bootstrap sample. So if we do that, table of .boot, look at the first, shows up here. So if you take a look at bootstrap sample to draw, observation 1, 2, and 3 show up at all. Observation shows up 1, 5 show up, 6 shows, 7 shows twice, through 13 show up at all, 14 once shows up 4. So doing the numbers 1, drawing 1, and then drawing another with until we get equal. And these are going to our sample. So because we're working with the index 1, create a boot sample for the and the out whether they voted. Treatment, just the treatment with the bootstrap, and the out is just vote outcome with bootstrap index. Create those new fields. And then what we do, calculate a different means for them. So we're going to contain and calculate the means. Let's see what that does. That's going to give difference in mean in the function of our difference dot 0.446. What it means is in the data we record a difference of 0.446 0.99, on the bootstrap sample, we get a limit of 0.444. So what we're saying, observe 0.99, we might have observed 0.444. That's a number that we reasonably heard to give. And what we're going to do is all of the bootstrap samples. Do that 1,000 times. It's on the next 10,000 times. And take the distribution of those. And here's our estimate. But distribution is going to give our uncertainty. And we need a loop. Okay. Want 10,000 lines of code where you just do 1,000 times in the same line 10 times. Let's look at this. This is the code for the self, where the container did it 1,000 times in 2 seconds. Draw an index bootstrap here. We create a variable, for that x. Then we calculate the difference in mean, store it in the container. So that's index, bootstrap outcome, and the difference in means. And we do that over and over again. When we do, we get the boot mean is 0.0403, and its standard deviation is standard error. Standard deviation of this is 0.153. Right? Now, we'll talk today in next lecture on how to regression to difference in means and standard error. Okay? What I want to do is bootstrap out the standard error, the one we get from regression. And then this line right here. Bootstrap estimate 0.0403. The gives us an estimate 0.099. That then this error from this 0.138, and here it's 0.0156. The difference, this is a long way bootstrapping and doing this over and over and over again. The process is done using an approximation. Assume that normally the means are normally distributed. And see is that the approximation is up nicely. If we were to do an approximation that the sample normally distributed, if we were to do this occasionally, get the from our bootstrap in this fashion, the two answers large agree on 3 decimal places, which is close. So what does that mean? I just include code plotting the boot distribution. So on the slide, we got our to be 0.039. Our bootstrap was 0.400. For science is the same number. Okay. And we have here an interim estimate of the treatment effect. Point estimate 0.099. The POL estimate ranges from here to there is the 95th. 2.5% of our bootstraps are over here, and 0.5% are over here. 90% of our bootstrap estimates fall in this region. So this is not just where the estimate is, but our uncertainty about it. In fact, just look at it. 95% mass of the boot distribution 0, and we'll later about start to call that really significant 95%. Introduce that normally, but it leads to intuition. We look at this uncertainty that we're generating with all the uncertainty. Look at this plot, see them, and if we do the 9% interval, it's positive, that concluding likely been a effect of the treatment. This is the point us, this point, all the bootstraps figure out the bell curve. So what does it look like as a figure. This figure you get for bootstrap, it looks normal distributed. Every time central limit, it's always sort of, that's a thing. The reason it's distributed is central limit there. Sample normally distributed. It's going to tell us regression functions are normally. The reason normally distributed is not accident, it's a consequence of the limit there. But using the first approach, we get 5% confidence interval of 0.09 and 0.700. That's the confidence interval around estimate, or the effective visited in person part of this experiment. So given this interval, we can conclude that there's a statistically significant POL effect or statistical down the line. But just following it, most of this, most estimated sample distribution is, so we're likely to get that there is a POL effect. Just comment how small, big. When in the social sciences, you generally want 3 significance. Hand in a number like 0.56-329, because this is not, we don't level percent anything. Some in our community advocates to 1 point, like 6. Ideally in that, there's not 6 significant digits. Okay, we're not tuning machinery. We're effective people indoors asking people to vote. Certainly 2 or 3 significant digits is about the way to get 1 or 2 decimal places. But really, you don't want 8 decimals on all your estimates. There's no one pretending at that level. All right, that's just present. So as mentioned in, when we were doing the bootstrap, one way to get this interval is to do the bootstrap. Require, you want to confidence, this would require a loop over and over any difference in want it to do. That's about as much fun. Okay. Rather than that, we're going to do a normal application, which is our sampling function. The distribution of our coefficient and differences are approximately distributed. In order to justify being normally distributed, that little curve. I mean, by all means. So what we're going to do is talk about how to use a regression to estimate treatment effect or a difference in mean and standard error. R is going to tell you automatically. So what we're going to do is we're going to take the person voted, treat for whether the item was visited in person, and we're going to use a model where this is the outvote tilde, and then the variable is a binary. We're going to linear model or regressive on a binary to get a difference. What we're saying is that outcome voted is an intercept plus a means time treatment variable plus an error. Another way to say it is if someone voted, we expect them to be beta 0 plus beta 1 because 1 in here. And if they don't vote, we expect there to be beta 0 because we put a 0 for here. Someone vote if someone's treatment group, if someone's in the group, plug in a 1 and their outcome to be hat 0 plus 1. If someone is in the control group, we put a 0 here. And so it zeroes term out, and we come to be beta 0. And what we can see is the difference in mean the treatment group control group is beta 1, which is estimated effect of the treatment variable. So what we're doing is using a linear regression to calculate the difference in mean. You don't need a linear regression like the calculated difference. The useful thing is the standard error. So in this case, if we regression, these results we get. Estimate is 0.038 and error is 0.015. Okay. And with that, we get confidence interval 0.098. Sorry. The confidence, we're going to take 0.09 and at 1 point track 1.6 standard. So we're going to take 0.03 minus 196 standard error and 0.389 1.9 standard error, would give us an estimate confidence interval of 0.98 and 0.070. That's awfully close to from the bootstrap. When we do the bootstrap long way by setting the sample certainty, got a confidence interval from 0.99 to 0.70. When we using estimate plus or 1.9 standard error, we get 0.00. What it's telling us is that if you're running a regression, the normal estimation work regression profile. It's an okay thing to run a 90% confidence. The estimate minus 1 point standard error. Let's calculate that. And for purposes, you can just call 0.96, or if you're doing the point though is bootstrap, it's not limited to means. Now flag this moment. Those who progress through 45, through 6, and through the certificate, at some point you're going to run to a statistical where you don't get a normal, you don't know how to get a good uncertainty. You want to, a present outcome, a sports game, something like that. And one of those to generate your estimate bootstrap. It's not limited to, it's actually a actual tool science. In that, if you have a black box method and you pick something like grow corporation, whatever nonprofit you want to predict, you can do a bootstrap, get an uncertainty. It's a generic method that works for uncertainty, not restricted in this class. It's a little bit useless, but it's not entirely for the model considering here because it's so simple. The normal notion works. You find yourself with a feed for neural network, random forest, something like that, line, then bootstrap is always certain guess that works reasonably well. Teaching it to you as a generic for getting on whatever you make down the line. So we do this in the normal approach using a little summarize. This is 0.03, so we're going to take the estimate and add and subtract 0.96 errors, and we get something that's through the bootstrap. But the estimate will work any model from this point for the rest of it. All right. One comment with this, if someone giving presenting a paper, doing a slide deck, have estimate uncertainty, rate and just ask them uncertainty on those are. If they say know how to it, ask them what to do a bootstrap. Getting the uncertainty estimates easily as getting a point estimate. Last few minutes, we're going to talk about indicator variable. An indicator variable, a variable that takes the value of one observation, in particular, 0 other ones. This is actually a really useful variable in sciences because our variables are categorical people in one number. So in this here for male or John, Mary, Beyonce, and Kim Jong, 5 years academia were examples of classes and random people. There's a cohort of students who were using examples from in one direction. That's one direction still. I know, like, broke up, like, I follow them, but like, do you like, they're good. Okay, we'll go back, maybe never. Case, an variable for male. John is probably male, a 1 male and a 0 female. Mary, again, probably female name, 1 for female, for male. Beyonce, a male, a 1 male, and Kim is male, a 1 for male, 0 for female. The point we can give people 0 or 1 based on whether some can do that. The point I leave you with is that plus female to 1. For those who are linear algebra, linearly dependent, know what one with the other is. It creates some wrinkles in our models, but for I think we're going to call it and structure.